Okay, one more example of solving an exponential equation using logarithms. And it's essential that you isolate the exponential part before you start solving. So you should divide both sides by 10 and have e to the 3z minus 7 equals 1/2. So then I'm going to find the logarithm of each side, the ln of e to the 3z minus 7 equals the ln of 1/2. And then I'm going to use the property of logarithms that says an exponent on the argument of the logarithm can come down in the front as a multiplier. Make sure and keep it in parentheses together. Well, now if you check with your calculator, you'll see that the ln of e is 1. Because e is the base, the ln of e is 1. So then we'll have 3z minus 7 equals the ln of 1/2. And then we need to solve for the z. So we're going to add 7 and divide by 3. So z equals the ln of 1/2 plus 7 over 3, and this is called an exact answer. And then if you were asked for a decimal approximation, you would say it's approximately 2.102. Okay, so then I have an example of an application problem. And we have that the amount of foreign earnings in trillions of dollars that's kept overseas by S&P 500 companies can be approximated by this exponential function, where x equals 5 corresponds to the year 2005. So we're asked to find the first full year, so that's solving for an x, in which the foreign earnings exceeds 1.5 trillion. So we're going to find when it equals 1.5 trillion and then say you have to go past that time in order to be over 1.5 trillion. Well, the only way to solve this is going to be using logarithms. So I first need to isolate the exponential part. So I'm going to do that by dividing by 0.227. So 1.5 over 0.227 equals 1.17 to the power of x. So now I'm going to find the logarithm of each side. And then use the property of logarithms that says I can bring this x down into the front as a multiplier and have the ln of 1.5 over 0.227 equals x times the ln of 1.17. So then we're going to divide both sides by the ln of 1.17. So we have an exact answer for x, but let's see what we get when we do a decimal approximation. And I'm getting about 12.03. Well, the first full year is going to be 13 years, because if you just put 12 in there, you're not going to get quite 1.5 trillion. So when x is 13, that looks like it's the year 2013. So that would be the first full year. Okay, so now we're back to section 11.8 to talk about derivatives of logarithmic functions. And the derivative of the logarithm of x is 1 over x. So that's if you just have plain x as the argument. So remember that the argument is what's inside the logarithm. So if the argument is anything but plain old vanilla x, if you have the natural log of some function of x, then the derivative is going to be 1 over the argument, don't change the argument, times the derivative of the argument by the chain rule. So it's not just arbitrary, it's what it has to be for the derivative to be the rate of change of the function. Okay, so let's look at this first example. Y prime is going to be the derivative of 10x squared plus 7 over negative 10x squared plus 7. So that derivative looks pretty easy. That's a polynomial, so I'm going to have negative 20x in the numerator and negative 10x squared plus 7 in the denominator. So notice that there is no ln anymore once you do the derivative of a logarithmic function. So then B I chose as an example to illustrate that you're going to want to be good at using the properties of logarithms to simplify and expand this logarithm, because you could do the derivative like this, but it would be a horrible job. Whereas if you write out the product, the quotient property of logarithms, you'll see you have the ln of 7x minus 1 minus the ln of 12x plus 5, and then each of those is really straightforward derivatives. So I'm just rewriting for now. I haven't done a derivative. Now I'm going to do the derivative. So I have the derivative of 7x minus 1 over 7x minus 1 minus the derivative of 12x plus 5 over 12x plus 5. So the derivative of 7x minus 1, 7 over 7x minus 1, minus derivative of 12x plus 5 is 12 over 12x plus 5. So this would be okay if we didn't need to do anything else with the derivative, but if we were asked to figure out when it was 0 and when it was undefined, we'd need to have a common denominator. These denominators don't have anything in common, so we just need to do the product of the two denominators as the common denominator. So we're going to get 84x plus 35 minus 84x plus 12 over 7x minus 1 times 12x plus 5. So that worked out nicely, that we end up with 47 over 7x minus 1 times 12x plus 5. So that's our derivative. Okay, then let's look at C, example C. And here again, I want to use the properties of logarithms that says the exponent can come down in the front and become a multiplier of the logarithm. And I haven't done any calculus yet. I have just done algebra, properties of logarithms. So now I'm going to do the derivative. And the derivative of a constant multiple is write the constant multiple and then multiply it by the derivative of what comes after. So the derivative of the natural log of a function is the derivative of the argument divided by the argument. So that's going to be 3 times 5x to the 4th plus 16x over 2 times x to the 5th plus 8x squared. And then I'm seeing factors of x in the numerator and the denominator. So I'm going to factor out x from the numerator and have 5x cubed plus 16 left. Then I'm going to factor out x squared from the denominator and have x cubed plus 8. So now one of these x's in the numerator cancels with one of the x's in the denominator, and I'm going to have 3 times 5x cubed plus 16 over 2x times x cubed plus 8. And if I asked you when this was undefined, you would need to factor the x cubed plus 8 as a sum of cubes to see when that was 0. Okay, then let's look at example D. Where we have y equals the ln of the square root of x minus 8. So in general, we don't want radicals when we're doing calculus. So we're going to change that into an exponent of 1/2. Well, then we want to use the properties of exponents on logarithms and have the exponent come down in the front and become a multiplier. Now we're ready to do the derivative. Y prime is 1/2 times the derivative of x minus 8 over x minus 8 . So that's going to be 1, because the derivative of x minus 8 is 1, over 2 times x minus 8. So there's my derivative. Okay, then let's look at combining this with other rules. So this first example, we have a simple function x, but that's a function, times this natural log function. So we need to see that this is a product and that the first function is x and the second function is the natural log of 9 minus x to the 4th. And then we need to use our product rule to find the derivatives. Well, u prime is simple. That's going to be 1. But v prime looks like it's going to be more complicated. So I'm going to come over here and do it separately so I can take as many steps as I need. So I'm going to have the derivative of 9 minus x to the 4th over 9 minus x to the 4th. So that's going to be negative 4x cubed over 9 minus x to the 4th. So negative 4x cubed over 9 minus x to the 4th. So then let's do our diagonal multiplication and get y prime is the ln of 9 minus x to the 4th plus negative 4x to the 4th over 9 minus x to the 4th. Okay, then let's look at example B, and I'm going to bring that over here where I have more space. Y equals the ln of x minus 3 inside of a square root. So I want you to look at this example compared to this example and see how they're different. In one, the square root is inside the logarithm in the first one. The second one, the square root's coming after the logarithm. So it's important that you see the difference there. So I can rewrite this example as the natural log of x minus 3, that whole thing, to the power of 1/2. The exponent can't come down in the front unless it's on the argument, and it's not here. So we're going to need to use the chain rule. And the chain rule is going to say I have something to the power of 1/2. So its derivative is 1/2. Don't change what's inside, to the new power of negative 1/2 times the derivative of the ln of x minus 3. So let's write this first part without a negative exponent. And then this is going to be times the derivative of x minus 3 over x minus 3. But the derivative of x minus 3 is 1. So my final answer is going to be 1 over 2 times the ln of x minus 3 to the 1/2 and x minus 3, and all of that is in the denominator. Okay, a couple more examples. C is a product of e to the x cubed and the ln of 4x minus 5. So u is e to the x cubed, and v is the ln of 4x minus 5. So then I need the derivatives. And for the exponential, u prime, it's going to be the derivative of x cubed, 3x squared, times e to the x cubed. Then v prime is going to be the derivative of 4x minus 5, 4, over 4x minus 5. And then we're going to need to do our cross multiplying. And we're going to have that y prime equals the ln of 4x minus 5 times 3x squared e to the x cubed plus e to the x cubed times 4 over 4x minus 5. So always when we do the product rule, we have two terms, and we need to look for a common factor, and we have e to the x cubed. So what's left behind is 3x squared ln of 4x minus 5 plus 4 over 4x minus 5. And that's about as simple as that one's going to get. Okay, then let's look at example D. And we have a quotient rule here. So we're going to have u is the function in the top, e to the x minus 1. And v is the function in the bottom, the ln of x. Then u prime, the derivative of e to the x is e to the x. V prime, the derivative of ln of x is 1 over x. So then we're going to multiply and get y prime equals e to the x times the ln of x plus e to the x minus 1 over x. Whoops, that's not the whole thing, is it? Because it's a quotient rule, so I need over the ln of x squared, and in fact, I need a minus, right? So we have a quotient rule. So we need to simplify this sum because you can't leave a fraction in a fraction as your final answer. So I'm going to multiply the top and the bottom by x and get x e to the x ln of x minus e to the x, and then this is going to be plus 1 over x times the ln of x squared. So that's your final answer. Okay, then I have one more example. And we have a number of internet users worldwide in billions. So this is billions of internet users. And x equals 15 corresponds to the year 2015. And we're being asked how many internet users are predicted for the year 2020. So that's going to be when x is 20. So we'll have f of 20 equals 1.2 e to the 0.062 times 20. So we're getting about 4.15 billion internet users. That's a lot. And then B says, what will the rate of growth be? That's a derivative. So let me rewrite f of x down here so it's close to our work. Okay, so the derivative of f, the 1.2 is a constant multiple, so it shows up again in the answer. Then I'm going to have the derivative of 0.062x, so that's 0.062 e to the 0.062x, and this is now in billion internet users per year. So it's the units of y, billion internet users, per units of x, years. Okay, so we're being asked now, what will be the growth rate in 2020? So again, we're looking at year 20. So f prime of 20 equals 1.2 times 0.062 e to the 0.062 times 20. And the instructions say round to 2 decimal places. So I'm getting about 0.26 So the number of internet users in 2020 is growing at a rate of 0.26 billion per year. So that's your interpretation. Okay, and that's all we have for section 11.8.